Thank you, Ian, very much. So I will try to convince you that the knowledge we got through conformal geometry some years back in a group of people, many of them are here with us, proved to be very useful for many more geometries as well. And actually, we saw a lot of this in Mike's beautiful lectures. And of course, I can't say but to admire that he has packed so much stuff in such a beautiful way in only 5 lectures. So I will just add a very tiny bit in a full lecture now, and let's see how much we shall understand. When I prepared the slides, I got a little bit afraid to come to the first main topic, Fefferman construction, because if it's related to the CR distributions of a very high codimension, I perhaps have to tell a lot about the geometry where it comes from, and therefore I will not have much time for the main part of the title. But I hope I will convince you that we are using a powerful machine which helps with such situations. So in the beginning, I will remind you a bit about the CR geometry in the perspective of the Cartan-Tanaka theory. Then I will mention what we heard about many times here. So that's the general machinery of the parabolic geometries, and then I come to the topic of the lecture. So whenever we start with a real submanifold in a complex space, then of course we can look at the tangent space, look at the conjugate vector space, and let them intersect, and that will also cut off a distribution in the tangent space, which is called a CR distribution, and I will denote it D in the sequel. And of course, for generic cases, so if we have the submanifold in a general position, then the rank of the distribution D will be constant, and the distribution will be generating the whole tangent space by brackets, Lie brackets of vector fields, and this is what we call regular CR structures. I will don't go for any other here in the talk. Of course, once we have the distribution, we can look at the associated graded tangent bundle. We add the quotient to the distribution, and this always carries a nice structure of a Lie algebra, and this is what the people call the symbol algebra for the geometry in question. Actually, there are very few dimensions and codimensions where the symbol algebras have to be the same pointwise locally, and if it happens, then we have a much more powerful machinery at our hands to study them in the way how Cartan did it already in the beginning of the century, following Poincaré's question, and which was then built into a full theory by Tanaka much later, although not very much noticed. And the oldest case, I wouldn't say simplest case, because the lowest dimensional cases always have higher homogeneities for the principal parts of the invariance in the curvature, so that actually you need many more steps in the prolongation to solve the equivalence problem. So the Cartan solution to Poincaré questions what are the biholomorphically equivalent hypersurfaces in Cn was one of the early examples of his general equivalence method, and this led later on to the general Cartan-Tanaka theory, as I mentioned, in the work of Tanaka, and also the much more famous Czermoser paper, which did it too. The hypersurface case is, of course, most important for function theory, and because it's just the boundary of domains, so you can read much of the properties of any objects you like out of its behavior of the boundaries, and therefore to understand the geometry of the boundary was so important. And Fefferman suggested years back a very fruitful approach which allowed to replace the much more complicated CR geometry by something much better understood, which was conformal. So I will have much less mentioning of conformal structures explicit here than Maria did yesterday. So I just made them bold. I think it will be only twice or three times in all the lecture. So the point is that Fefferman built a natural circle bundle over the CR hypersurface, which naturally was equipped with a conformal structure, and because it was a geometric construction, so all the invariants, all the natural objects for the conformal structures were in some well understood relation to something on the CR geometry side. And the title of my talk indicates that I want to come up with something similar for different cases of CR geometries. The higher order codimensions seem to be hopeless because in general you always have smooth families of non-isomorphic symbols at your disposal. So if you take a generic case of a surface, you end up with different symbols at each point, and that makes the life a bit more difficult. Of course, there are approaches, and Igor Zelenko definitely would not agree with me that it's hopeless because they have solved as good as all the situations, and they don't mind to have changing algebras there. But the outcome is no way similar to what we get with these rigid cases because you get a canonical coframe which solves your Cartan equivalence problem, but it's no more a nice connection-like thing, and you don't have a calculus which would allow you to work in a similar way how Mike was showing us for conformal, projective, and other parabolic geometries. But still, you have a good chance to work in a very similar way if you add a requirement that the symbols will be the same at all points. And that happens quite often in interesting cases. For example, if you deal with Shilov boundaries of homogeneous domains, then you get higher codimensional things, and then still it's not belonging to what we call parabolic geometry because the group structure, the algebraic structure coming out of the symbol is different. But there are some exceptions, so very little exceptions, very few exceptions. One of them is the special case of six-dimensional real manifolds sitting in C4. And there you have only two stable symbols. In fact, you have three symbols: elliptic, hyperbolic, and the third one is called parabolic. And the situation there is somehow very special and is related to these low dimensions, because what you get there is you can aside of the real cases, you can deal also with the complex versions, and you can either see it as complexifications of the real situation, or you can add some more flavor, like saying that there is additionally a complex structure there, and then you have many more torsions there and curvatures which are responsible for integrability. And in this particular case, you have two ways how to see homogeneous models. One of them is you take the three-dimensional thing, which is already due to Cartan, but you understand it slightly different. So you either take it as a complex, so over C, which means it's twice as many dimensions there, and you end up exactly in six-dimensional gadgets sitting in C4, or you can take the real situation, but you take it twice. And you are discussing things which are modeled over products of three-dimensional surfaces, each of them in C3. And then this is the elliptic case, this is the hyperbolic case, and it has got a very beautiful geometry. you have got 6 torsions and 2 curvatures there, and everything can be computed absolutely explicitly in terms of coefficients in a normal form, and it's just absolutely explicit description, and the parabolic machinery is very essential there. So the other case is what I will be talking about today. It's 2n plus n square dimensional thing in a big dimension of Cn, and that's what's called the n square codimension CR manifold. So for example, you have the simplest situation of M3 sitting in C2. The next one for n equals 2 is M8, 8-dimensional thing sitting in C6, 15-dimensional manifold sitting in C12, etc. So it's an infinite series of interesting dimensions. And in this case, it's absolutely rigid. You have just one type of simple algebra available. So the 6-dimensional case, which I was indicating, was studied in great detail in our joint paper with Gerd Schmalz. And actually, the current project is ongoing from that time, because we knew that there will be one more example, but we never came back to think about it in detail until 2 years back, when we just sort of thought it's highest time, and it had some other reasons I will come to, and so it's still in progress.
So you're going to explain to us why that's a good codimension?
Yes, I will. Before coming to the point why it's a good codimension, I will remind you a little bit of the general theory of Cartan connections, and in particular the parabolic cases. So we heard it in the conference in several lectures already. So I just remind you that Cartan connection is a very particular example of the result of a procedure following Cartan's original approach, where you are able to build a coframe which is not only step by step prolonged until there is no freedom left, but you also can guarantee that all these individual steps will be matching nicely together to a group action of a structure group, and therefore you end up with a coframe sitting at a principal fiber bundle and having much nicer properties, which is a particular case what Cartan would call absolute parallelism and connection, but it's adopted in the nowadays literature to be called Cartan connection. So it's in certain sense a special case of what could be a Cartan connection, and we call this object Cartan connection. And it's also possibly viewed as a curve deformation of the Masaryk-Cartan form of the homogeneous space, because you just mimic as much as possible of the properties of Masaryk-Cartan form, which makes sense on a principal fiber bundle instead of the homogeneous space G over G mod P. And just to understand the flavor, and also to give us a better understandable exposition of the procedures I will go into in a minute, I will just illustrate the concept of the general parabolic geometries on this example. So the example deals with rank L distribution on a manifold where the complementary subspace is exactly as big as the space of antisymmetric matrices. So if you imagine what it means, it just says that if such a distribution should be regular in the sense I used for the CR structures, it means it's bracket generating the whole tangent space, then and it should be bracket generating the whole tangent space just in one step. So not like we saw in the G2 case, where we have this 2, 3, 5. Here we want to have L and the whole lot. Then, of course, what it means is you have the Lie bracket of vector field change into a matrix of antisymmetric 2 forms, and the matrix should be just of highest possible rank, and it's a antisymmetric 2 by 2 matrix. So the dimension is exactly the dimension of how many forms you have, and therefore up to a GLL action, there is just one possible symbol. So all the symbols will be the same up to isomorphism as soon as it's non-degenerate. So therefore, this is such a good example. The lowest dimensional case was discussed by Robert Bryan, so it's a three-dimensional distribution in six-dimensional manifold. And this is just a general series of the same thing. Of course, the lowest dimensional case, again, has completely different structure of curvature, as always. Yes. So there is a general theory of all such situations where you just model your associated graded tangent space over a nilpotent algebra such that it's just the nilpotent part of a parabolic subalgebra. And this is what we call parabolic geometries. And this is the infinitesimal way how to define such a structure. And only sometimes you have to add some more structure. But the question whether you need some more structure or you don't is governed by one of the cohomologies, and it's just the so the case we are dealing with now in the example is just a parabolic geometry which belongs to SO case, and it's this one. So you see that the Lie algebra, I will take it's the split form, so I will say the antisymmetric thing along the anti-diagonal. So here will be just zeros, and this part is defined by the upper one, and what you get there is a, wow, that's not the best way how to put the line there. Something like this. So here is 0 in the middle, and here you have this RL, and it's Q-symmetric. Downstairs here, so here is lambda 2 of RL, and that's the model algebra for the symbol. And the cohomology which in general settles the question whether you need more structure is the first cohomology of G minus with values in G. And actually it's a quite simple exercise to show that the automorphism group of the filtered algebra is the whole lot of G0 if and only if the cohomology components appear only in the negative homogeneities. And you need some more information if it appears to homogeneity 0, and there are no other homogeneities. So in this case, you just look up in some software or you compute by hand, and you see immediately that there is no further structure. It's just defined by the distribution itself.
So what is the harmonic part of that curvature?
Yes. So I mean, in general, the Cartan connection is a one form sitting at a principal fiber bundle this way, and omega is in it's in one form of G valued in G, and the curvature d omega is just defined the usual way, so it's just minus the bracket omega plus the curvature, and you can write the curvature also as a curvature form just using the absolute parallelism omega, and then gives you curvature as a function valued in lambda 2 G minus upper star tensor G. And just hold the normalization procedure, which I didn't want to talk much about, shows that there is just one canonical Cartan connection for all initial data, is based on the fact that if you look what happens if you change your connection upstairs so that the filtration downstairs doesn't change, then you compute that the respective change influences the curvature by something in image of del. And because you are in the nice situation, there is also the del star, so there is a obvious way how to normalize the things to require that the codifferential of kappa is vanishing identically, and therefore out of Bianchi identity and this, you then immediately see that the harmonic part of the curvature with respect to the Laplace, so this Hodge Laplace operator on the cochains produces the invariants, which are the essential invariants.
Yeah, so the short answer is, just to make sure I got it, is harmonic refers to the Lie algebra.
Cohomology, yes. Yes, that's the Lie algebra harmonic. Okay. So if you compute the cohomology, you see that this is the only one. This is the only one, and therefore it must be just this. And then of course, because you know in advance what happens, although it's just quite a messy situation, you are able to run the very regular standard Cartan approach to the exterior calculus, and you compute the prolongation. And in particular, you need only to do the first step, because you know in advance that the principal invariant will sit in the homogeneity 1 part, and you complete out of your structure functions. If you just give your distribution somehow, you get it for free automatically. Well, not for free, but explicitly. Just it's a matter of calculation. So that's an example just to show you on something, well, easily understandable how the general theory operates. Now, what about the free CR distribution? So that's the Nsquare codimensional stuff. So actually, it turns out that it's very similar to what we saw here in this particular example. We just have to replace antisymmetric with skew Hermitian. And that's exactly what's happening on the level of the N-square codimensional CR manifold. So you just pick up your nice group SUN plus 1n with this particular grading. So it's exactly the same grading as here, except I just take another parabolic subalgebra. What I get there is just this one. So this is the subalgebra in question, which defines the parabolics, and the grading associated to that is exactly this one. So it means it behaves in a certain sense very similarly to the hypersurface geometry, except instead of having columns 1, n, 1, you have columns n, 1, n. And behaving exactly as you know from the hypersurface case, you would think of building the whole geometry. Then the first thing which you get stuck with is the fact that, unlike in the hypersurface case where it was just the distribution, so the contact distribution together with the complex structure which defined your geometry. Here, if you compute the cohomology, you find out that there is no cohomology, the first cohomology in homogeneity 0, and therefore everything must be completely fixed already by the distribution itself. So how about with the J's? But it's a very simple observation actually, just looking again at elementary linear algebra, that if there is a J making the Levy form, so the Lie bracket, into a totally real antisymmetric thing, then the J is given uniquely up to conjugation. So it's actually a very, very rigid condition to admit a J for a distribution of the right dimension, so that there is a way how to make the values Hermitian skew symmetric matrices. So that's the answer to the seemingly unpleasant problem, which is actually just an observation. And the next point is also very, very sort of interesting, because if you compute the second cohomology, you find out that there is one component in homogeneity 0 and one component in homogeneity 1. And of course, we do not allow homogeneity 0 in general for the construction, because the original way how people following Cartan look, the thing is you start with some Pfaffian system and you take the Lie bracket of vector fields as the algebraic generator of the symbol algebra, and you want to have it just equal to your symbol algebra in the geometrical structure, whereas the homogeneity zero curvature would say you that actually you have got two brackets, and the difference of the two brackets is just described by the cohomology. One which comes from the vector field and the other one which comes from the structure. And that's something we also try to discuss with Stuart Armstrong, but it's not yet finished. It's actually his research, not mine. I could come back to that later if someone is interested. So here, the good news is that the homogeneity zero says whether there is just exactly the bracket you get from vector fields, whether it allows a J from the lemma. And if we restrict ourselves to the embedded things in Cn, so we get it granted that such a J will always exist. So it's just a good way how to producing such nice distributions where the zero cohomology and the responsible curvature of that will not show up. And therefore, we can adopt an abstract definition for what we could call an integrable case, so the case which corresponds to embedded surfaces. And you take a smooth manifold of the right dimension, you take a 2n-dimensional distribution such that it generates the whole lot of Tm, and we call the a free CR distribution of dimension n if there is a complex structure J such that the algebraic Lie bracket is totally real with respect to this particular J. And we know from the lemma that such a J is defined uniquely up to conjugation, so either J or conjugate J will do. And the essential lemma from the point of view of the general theory is that every such distribution provides a defining infinitesimal data for what we call a parabolic geometry, and we call it a regular infinitesimal flex structure in our book with Andreas Chapp, which was also mentioned already here. And so, therefore, the general theory applies, and we know that for each such CR distribution there is just one canonical regular normal Cartan connection, and the only fundamental invariants of the free distributions are concentrated in the curvature of homogeneity 1, it's just the simplest torsion you can ever dream of, and they correspond to the totally trace-free part of this particular submodule. The case n equals 2 is slightly different because there you get two homogeneity 1 torsions, so there is no homogeneity 0 thing. And the other one is the Nienhuis tensor of the complex structure J. So this vanishes for the integrable case anyhow. So that's for the 8-dimensional manifolds in C6. And moreover, just out of the general theory, you see immediately that every smooth map between two free CR distributions which respects the distribution is automatically either a CR morphism or a conjugate CR morphism. That's the general result. So what is the homogeneous model now? The homogeneous model is, of course, what you would expect, just the quadric. You just take n square quadrics and intersect them. And that's it. That's the Q. And you can build it in the standard way, like that. Take the isotropic planes and the isotropic subgroup of one of them, and you take the homogeneous space. And of course, then no, I mean, this is what you get. This is just the choice of the homogeneous model. So and if you compute a little bit in detail, you see that really on such a homogeneous model, you automatically have the distribution of the right dimension, and it's non-degenerate, and therefore, out of the general theory, you get absolutely for free what's called the Liouville theorem. So you see that the group of all local automorphisms of the quadric is just the same as the group of global automorphism, and it's just PSU n plus 1n. So people like Gerd Schmann were having big problems to prove these things explicitly, just as the way the function theories do. So here you get it as a very, very simple corollary of the general stuff. Just to have a glimpse how you can compute then the invariant, and I do it because I needed to start then also some exposition or to proceed towards the Fefferman construction. So you just do the exterior calculus the very standard way. So you pick up your favorable local frame, which will be chosen in such a way that you complexify the tangent space. So you take any commuting local frame for the distribution, well, D01, say the one of those two, which you get, and you take the conjugate axis at the other half, and you take all the brackets of one holomorphic and one anti-holomorphic fields, which will provide you, because of the non-degeneracy, with Nsquare independent, linearly independent fields in the quotient, and therefore you get a nice suitable frame. You take the dual coframe, you restrict it to the original real manifold, so that's what I call theta I, theta jk, and the bracket is indicating skew Hermitian. Of course, you have the d perp, which is generated just by these forms. And you can write down the structure equation. Some of the terms are missing due to our choices. I will not go into the details, but still you have a lot of ugly functions there. And you can, fortunately, proceed very quickly. So because you know that there is a normal Cartan connection, you just move at the same time from bottom to top, like in the classical approach to Cartan equivalence problem, and from top to bottom, because you know the result in advance, so you just want to compute it. So you just take an arbitrary section S and you want to adjust S so that to normalize the thing so that you know, in such a way you know the result has to be. So we get, choosing any section, we get just a matrix of one forms, and we know already some of them because the omega ij, just due to our choices, is the same as the original thetas, and we also know that the omega i's are the theta i's up to something in d perp. Now, if we take just the general thing we can think of, so how to change the omegas to make them more right, well, actually the C's are a way how to describe a choice of the complementary n-square dimensional subspace. So that's the meaning of C's. Whereas here, the G not valued part of the matrix describes the choice of the partial linear connection in the sense, well, similar like Webster-Tanaka connection, but you will be able to differentiate only in the d direction, so that's the homogeneity one part of the Webster-Tanaka in this high codimensional thing. And now the additional freedom in G1 allows you to kill the trace of A's. So it's just, you could also move different way, but that's something like a special choice of the connection you are constructing. And then you evaluate the curvature. So you see that the curvature will have to be something like this. So the A's, B's, and C's appear there, and the torsion is this one. So it's the homogeneity one part of the torsion, which eats only the elements from D. That's what I'm now interested in. And you can evaluate the Q's, and by the general theory, you know that the Q's have to be zero, because there is no harmonic part like the Q's. So you immediately see that vanishing of Q's allows, and vanishing of all traces of P. So we know that the P is trace-free, and we know that the Q's are just vanishing. And using that, you can explicitly compute out of the structure equations what the A's, B's, and C's are, and therefore you just have chosen the homogeneity one part of your Webster-Tanaka connection together with the splitting. The difficult point here is that you can't do it separate. You have to do the splitting together with the choice of the connection. So that makes a big difference to the hypersurface case. So what could we do next? So of course, the obvious procedure will be to exploit the freedom in G2 and then continue for homogeneity 2 thing and normalize the things again, because you know what parts of the curvature have to vanish and what are the properties. And so this would lead you to a completion of the Christoffel symbols for the analog of the Webster-Tanaka connection. And also you will get the homogeneity 2 part of the so-called row tensor, as Mike was using in his lectures once, I get. And so on. So you could move on and following the scheme like it was done, say, in Chern-Moser paper, just compute the whole matrix, and on the way you would compute all the rows. Already in the second step you would have all the connection part ready. But there is an alternative way. The alternative way is to mimic the original Fefferman construction of the conformal structure on the canonical circle bundle over the CR geometry of hypersurface type, and then you get a one-graded geometry, or you did in that case, and you can understand the thing so that the rest can be read off these data then. And in order to construct the Fefferman space, you need only the prolongation of homogeneity 1. You don't need any further data. So we've done already enough to try to mimic the construction now, and that's what we shall be doing in the last part. So how many minutes I have? I think I started a little bit later, so should have something like 8 minutes. I don't know. Well, you are the boss. Yeah. You stop me then. Yeah. But I think it's just exact 8. So before I go into the details, or I don't show you much details, but before I go for the description of the Fefferman construction for the high codimensional CR guys, let me remind you or introduce you, depends, to how you may understand the Fefferman construction as some very nice categorical functorial construction, which is well understood at a homogeneous model, so well understood at a homogeneous model that you immediately see it works also at the curved situation. And so the setup is the following. You just take 2 parabolic homogeneous spaces. Actually, you don't need parabolic, so you just take 2 homogeneous spaces, and you request the following assumption. So you just want to embed the G into G tilde, I will call G the small one and G tilde the big one, in such a way that the embedding would be infinitesimally injective. You want to have nice way how the G orbit of the beginning of the new space, what I will be calling bigger space, is behaving. So you just need that if you compose the infinitesimal embedding of the algebra into the bigger algebra, and you quotient out the new P tilde, so the structure group, then you want to get a surjective mapping. So it means that you will end up with some open sets where you need to construct some structures. Otherwise it wouldn't provide you with nice geometries. And the last requirement is clear. You need that the original structure group P contains the preimage of the new structure group in the embedding. So you can understand in such a way that you simply have your G, which is over G mod P, and then there will be some smaller group P, so the G mod Q will sit over the G mod P. And on the top of that, you have some G tilde, and you have the embedding here. And the G tilde will be sort of providing Q with some new geometry over G mod Q. So it's sort of composition of 2 obvious functorial construction, what we call correspondence spaces, that's the first bit, and what we call group extension, that's the second bit. So what are the consequences? So of course, so I partly told them already all. So there is the natural projection, that's this one, Q must be a closed subgroup of G, which usually is no more parabolic. The homomorphism induces a smooth map from G mod Q to G tilde mod P tilde. So we have got this map here. And the letter open space in G mod tilde or P mod tilde carries a canonical geometry of the new type. So we can just pull it back to get the same geometry on this one. So that's the main ingredients of the construction. And of course, in the originally, so hypersurface CR, so the hypersurface CR case, you see you just take this group, you have all the others there as well, and you embed it in the corresponding SO. So it will be, so this is, yeah, so it will be an, yeah, I will not care about the signatures here. So in our case, so in the original Fefferman case, of course, you were exactly in such situation. So you took this one and this one. In this particular case, we can build the same thing, and what you get is you embed it in a little bit bigger guy. Just you split the double edge into two edges, and you just embed it in such a way that you double the middle column and provide it with some coefficients so that to make it into a Lie algebra embedding if restricted to P. So while in the hyper-CR case, the embedding here of the SU P plus 1, Q plus 1 to the corresponding SO group doesn't give you such a case where Q would be P because just the imaginary part of the center in the linear part, in the semi-simple part of the Levy decomposition is staying out of Q in P. So you just are left with exp of IR, and therefore you get the circle bundle there in the Fefferman case. Here in this free distribution case, it's one of the miraculous cases where P equals Q. So you get a new geometry over the old one, and the new geometry is this one. So it's just in the lowest dimensional case where, because of the D4 triality, it's again a conformal geometry. So I've got a third conformal today. In all higher dimensions, it's just a different geometry. So we talk about inclusions in this special case, and the inclusion wasn't the case in the original Fefferman construction. You got a bigger bundle, but not much bigger, just a circle bundle. What about our case? Our case is very similar to what we did with Boris Dobrov. So simply, instead of skew symmetric, we take skew Hermitian, and we obtain a similar embedding. The only difference is that with Boris, in the SO case, so here what we get is we just take this guy with some other knots here, and we embedded it into a slightly bigger guy where there will be only one cross in the middle, but we add one white cross to each side. So there will be actually this way, and again there will be the crosses everywhere. So this is what doesn't have a name in the literature yet, although it's also a boundary of some well-known homogeneous symmetric domain. So you see the difference between the SO case and this SU case is that in SO case, there were zeros here on the diagonal. So there were also 4 zeros here in the embedding, and therefore, when looking at the inverse image of P, we got P tilde, we got just the whole lot of P. Whereas here, there will be just one piece staying aside, and that's again the purely imaginary thing in the middle here. So again, we are ending in exactly the same situation as in the original Fefferman construction. We have got a circle bundle over each our free CR distribution, equipped with a what we call, just by pure analogy, Hermitian spinorial geometry. So that's the one-graded geometry which is given this way, and if we want to see it, how it looks here as a matrix, so it's just this. So this is G minus 1, this is G0, this is G1, and it's all skew Hermitian. So the geometry is defined by means of an auxiliary bundle of dimension L plus 1, so that the tangent space is identified with the skew Hermitian matrices of rank L. So this is, as I told in the beginning, this is still a work in progress, in particular the last bit. So there are many things to do. So for example, we are seeking for the right name of these structures, these Hermitian spinorial structures, because I even don't like the spinorial structures as the name for the SO1 graded geometry, because it's somehow very, very far from being spinorial. It's just only the position where the cross is placed is corresponding to the spinorial representation, the fundamental representation, but I don't know more clues. Of course, there are more interesting, more important questions. So the second one is the crucial one, because the functorial construction always provides a extension of the original Cartan connection on G, where you know it exists, to a new Cartan connection here. It's the extension, but it need not be normal automatically. So in the SO case, we proved with Boris explicit theorem saying what are the curvature obstructions, and there are examples of special distributions which satisfies the obstruction. So you have a special class of surfaces which produce automatically the normal connection. But of course, even if it's not, it should be even more interesting, because you always, in a functorial way, produce the spinorial skew Hermitian structure. So you have the two normal connections there. Well, the normal connection and the induced connection, and their difference must be something very interesting, because it's an invariant of the underlying surface. So that's the second question, and a lot of work there, because it's sort of not very simple formulae you deal with. And the third one I find even more interesting, because on the one-graded geometry you again have a nice class of curves which behave exactly as null geodesics for conformal geometry. They correspond to the elements in the G minus 1 in the Lie algebra, which has lowest possible rank as matrices. And then of course projecting them down must provide you with full analogy of chains in the hypersurface CR, because that's one of the ways how you can define the chains. Whereas here, having Nsquare codimension, it's perhaps quite difficult to guess what they should be in a direct approach. That's it. Thank you very much for attention.
Questions for Jan?
Please.
Okay, how to recognize these couples, G prime and P prime, like G is acting transited
I mean, normally, we never try to classify them. There definitely could be a good possibility, say, to classify all where you get just circle bundles. and etc. So we wrote in the paper, so originally the motivation for the paper with Boris was to classify all where it's just the inclusion. And that's possible. Up to some question raised by Robin, it's solved. So we never try to answer questions what are all possible couples of G and G tilde. But the Fefferman-like constructions appear simply by themselves, and then whenever you see something similar, it's a good idea to check whether it comes from such a functorial construction. So for example, what we heard about the conformal structure for the G2, it's another example of such an inclusion. So it's very easily understood this way.
Besides the ones that are just inclusions, where the Q is also a parabolic subgroup. So, I mean, are there any interesting known examples of geometries besides this one and just the inclusions?
I haven't seen any. Well, even in this case, Q is not a parabolic subgroup. It's just rather a question whether P tilde is parabolic subgroup, and we would perhaps find quite a few examples of that type. But I know only the inclusions ones where the Q itself is again parabolic.